Okay, so here we are with the second part of lesson 1, and this time we're talking about a circle's radius grows at 3 inches per second. Now, as soon as I see that, I'm going to think about rates, because 3 inches per second is a rate. So I know that my radius is growing at a rate of 3 inches per second. The problem tells us to find how fast the area is increasing when the radius is 5 inches. Okay, so this problem is much like the square problem, where as the radius gets bigger, the area grows much faster. So when the radius is smaller, the area is growing at a slower rate, and then as the radius continues to increase, the area of the circle will increase much quicker. Okay, so I would encourage you to again turn off the video, go to the website that's on the front page of your notes there, and check out the applet and see what's going on here. Okay, so I'm going to take a look at this. Maybe, there we go. And we're just going to take a look at what we've got, what's given to us, and what we can do with this problem. Okay, so it says, first of all, what rate are you given? Okay, so as soon as I see this, again, I saw that the radius grows at a rate of 3 inches per second. Well, that means that dr dt, okay, dr dt, so that's the change in the radius with respect to time. Dr dt is 3 inches per second. Okay, so that was a given rate that I can use later on. What rate are we asked to find? We're asked to find how fast the area is increasing. So we're asked to find dA dt. Okay, this is the question. What is dA dt? It says, what other info are you given? Well, it tells us that the radius, they want us to find the rate of change in the area when the radius is equal to 5 inches. Okay, and what other info can we get from the problem, and what formulas will you need? Well, in this case, we're talking about area of a circle, so we know that we might be able to use area equals pi r squared, area of a circle. Okay, now a lot of people might be tempted to say, well, since the radius is 5, let's just plug in 5 first. And the problem is that you cannot do that. You cannot substitute 5 for r, because, and this is going to be in every problem that we do, because the value of r is changing. The radius is changing. So I can't just put in 5 and say, okay, what's the area? Okay, if I plug in 5 right now, that's all I get is the area. I want to know the rate of change of the area. So in order to find a rate of change, we need to take a derivative. So we're going to take d dt, we're going to take the derivative with respect to time of a equals pi r squared. Alright, so that's dA dt equals, now we're going to take the derivative of the right side, so taking the 2 down in front, that's going to be 2 pi r times the derivative of r, so that's dr with respect to time, dt. So you can see that now by plugging in 5 for r, okay, so let me make some notes over here. So now that I have my formula for rate of change of area, now I can plug in my value for r equals 5, and I was given dr dt, and dr dt was equal to 3. So here we go. That means that the rate of change of the area with respect to time is equal to 2 pi times r, which is now 5, times dr dt, which is 3. And so my rate of change of area is, what do we got here? 30 pi, and our units are in inches again, so this would be area is inches squared, and our time was in seconds. So what we are saying here is this: when the radius at the exact point in time when the radius is 5 inches, okay, the area of the circle is increasing at a rate of 30 pi inches squared per second. Okay, so at that exact instant in time, our area of our circle is increasing at a rate of 30 pi inches per second. All right, let's take a look at another one here. What do we got coming up next? Okay, so we've got another circle problem here. It says a circular pool of water is expanding at the rate of 16 pi inches squared per second. Okay, so this time they're giving us the rate in which the area is increasing. Notice the units here, 16 pi inches squared per second. Okay, so that circle, the area of that circle is increasing at that rate. At what rate is the radius expanding when the radius is 4 inches? Okay, so when the radius is 4 inches. Now, so what we're going to do is we're actually going to look at the applet for this one. And so I'm going to go to the applet page at GeoGebra here. And what this graph is showing us is the radius versus time. So how big is the radius versus the amount of time that goes on. Now keep in mind that the area is growing at a constant rate of 16 pi inches squared per second. So watch what happens as time goes by here. So you can see the area of the circle growing, the radius is getting bigger and bigger and bigger. And the area of the circle continues to grow, the radius continues to get bigger, but if you notice, the rate of change of the radius is slowing down a bit. Okay? So it starts out relatively fast, but then the actual radius itself does not grow as quickly. Okay? So when this thing starts over again, we're going to stop it, and we're going to show you what this graph actually looks like with the rates of change. Okay? All right. So let's see if I can reset this. No. Oh, come on here. Let's see what's going on. Why can't I reset? I'd have to reset the page here. Okay. All right, so this time I'm going to show the graph with the tangent line, and I'll talk about it as it goes up the second time around here. So we've got our function. There's the graph of the function as time goes on, the radius changing. Now watch the dr dt this time. Okay? So you'll notice as time goes on, the radius, the length of the radius, it doesn't grow as quickly. So dr dt is actually a lot less at the end. Look at dr dt. I'm going to stop right here before we get to the end. Dr dt is 0.31. That means that the radius is growing at a rate of 0.31 inches per second. Okay? Look at it. What happens when it starts down at the beginning of at the very beginning near zero. Look what the rate is down there. So we're going to let it finish out. It's going to jump back down and start over. Look at the rate right there. The radius is now growing at a rate of 1.63 inches per second. But then it starts to slow down very quickly, even when we get to roughly 10 seconds right there. The radius is now growing at a rate of 0.62 inches per second. Okay, so the actual rate that the radius is growing is slowing down. Okay, so we're supposed to find out at what rate is the radius expanding when the radius is 4 inches. Okay, so here we go. Let's grab our pen again. All right, so number one, what's given? Okay, what's given? Just like last time, they gave us a rate. This time the rate was the area. They told us that dA dt was equal to 16 pi inches squared per second. Okay? Number two, what did we need to find? We needed to find dr dt, the rate at which the radius is expanding. Number three, what other info? Well, they want us to do this when the radius is equal to 4 inches, and they want us to do this when the radius is equal to 20 inches. And we will do both of those. And I think in the last page it talked about what other information can you get or what information do you need. I'm going to put my area formula in here as well. So area equals pi r squared. Now again, I cannot plug in 4 in this case because I don't plug in, if something changes, I don't get to plug it in until after I take the derivative. Okay? So we're going to take the derivative, d dt of a equals pi r squared, just like we did in the last one. So we have dA dt equals 2 pi r dr dt. Okay, so that's our formula for finding either the rate of change of area or the rate of change of the radius. In this case, we were asked for the rate of change of the radius, and we were given the rate of change of area. So we're going to start off when r is equal to 4, but the one piece that we were given was dA dt. We know that for both r equals 4 and r equals 20, that dA dt is going to equal 16 pi, and I'm not going to put the units on there because we're going to plug that in right now. So dA dt is going to be 16 pi equals 2 pi times the radius, which is 4, times dr dt, which is exactly what we're trying to find here. So 2 pi times 4 is going to be 8 pi, so we've got 16 pi equals 8 pi times dr dt. If you divide both sides by 8 pi, you get 2 equals dr dt. What does that mean? Okay, first of all, we need some units. All right, so dr dt equals 2, and this is the radius, so this is inches per second. So what does that mean? Okay, what that means is this: when the radius is 4 inches, okay, so when the radius is 4 inches, the radius is expanding, okay, getting bigger, whatever you want to call it, expanding at a rate of 2 inches per second. Now, as you saw in the video on the applet, the radius actually grew at a slower rate as it got bigger. Okay? So that's what we're going to see when we do r equals 20 right now. So we're going to do r equals 20. Do some purple here, so now we're going to do r equals 20. We don't have to change the formula because the formula is the same. So dA dt stays as 16 pi equals 2 pi times the radius. Now we get to drop in 20 times dr dt. And then again, we're just going to solve for this. So this is going to be 40 pi on both. So we have 16 pi equals 40 pi dr dt. So if we divide out 40 pi on both sides, let's do this. I'll just 40 pi here, 40 pi here. That's going to leave us, the pi's are going to cancel, and this is going to leave us with 2 over 5. Divide both of those by 8. Now again, I'm going to attach the units right away here because this is 2/5 inches per second equals dr dt. So you can see that the radius has slowed way down in its growth rate. Okay? So when the radius is 20 inches, okay, the radius is expanding at a rate of 2/5 inches per second. So it's expanding at a much slower rate than it did when the radius was 4 inches. Okay? And that's what a related rate is. Okay? We're relating the rate of the radius to the rate of the area. Okay? All right, so if you flip over to page 8 in your notes, you'll see this picture, and I'm actually on the GeoGebra applet again. So the scenario this time is that we have a 13-foot ladder leaning vertically against a wall. If the bottom of the ladder slides away from the wall at a rate of 2 feet per second, that's a key term there. Okay, anytime they say at a rate of or give you a rate, you want to keep that in mind. How fast is the top of the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? All right, so I'm going to play this and just kind of watch, you know, as the bottom of the ladder slides out, what do you notice about the top of the ladder? How fast is it falling? Okay, so the bottom of the ladder is moving pretty quick there, but the top of the ladder is not going very fast at all. But as the bottom of the ladder goes further out, the top of the ladder starts to move a lot faster, you can see. Okay, so as time goes on, we have this ladder falling. Now I'm going to show you the curve for this, and we'll talk about that. So we're going to go down and boom. So here's our curve. You'll notice that the curve has a much steeper slope as time goes on. So I'm going to stop it up here. Take a look at the rate of change in the height of the ladder. So dH/dt is negative 0.046 feet per second. So that's a pretty small number right there. And you'll notice it's negative. Why is it negative? Because the ladder's falling. The top of the ladder is decreasing its distance to the ground. So therefore our rate is negative. Okay? So when we talk about this, we're going to talk about the ladder falling at a rate of, in this case, 0.046 feet per second. Now, as the ladder starts to get pulled away, you'll notice that the rate starts to increase. So if I stop it a little over 2 seconds here, at 2 seconds in, then now the height of the ladder is falling at 0.719 feet per second. So the top of the ladder is starting to fall a lot faster than it was at the beginning. And if we go on, you can see that our rate ends up increasing a lot by the time we get down to the bottom. Look at that. So at 6 seconds, our ladder's falling now at a rate of 5.434 feet per second. So as the bottom of the ladder gets pulled out, the top of the ladder actually falls faster. Okay? But what stays consistent, if you read the scenario again, it says if the bottom of the ladder slides away from the wall at a rate of 2 feet per second. So the bottom of the ladder, the rate is consistent. It's the top of the ladder where the rate changes. Okay? So we're going to go back and take a look at this. I forgot to flip my page here. So here's our scenario on page 8. And so we're going to take a look at how to set up this problem. Okay? So, like we saw in the video, the top of the ladder falls faster as time gets bigger. As t gets bigger, the top of the ladder is actually falling faster. And we talked about the fact that y is dh dt. Why is this vertical distance and why is this rate a negative value? Because the distance from the top of the ladder to the ground is decreasing. Okay? The ladder itself does not change length. Okay? This is a consistent 13 feet here, and the rate is a consistent 2 feet per second. So let's talk about given information here. All right? What are we given? First thing we noticed was the rate. Okay? The way they have this labeled here, they're labeling the bottom as x. So we're going to call this dx dt. So the rate at which the ladder is being pulled away from the wall is 2 feet per second. Okay? We were also told that the ladder is 13 feet. So I'm going to call that, since we're looking at a triangle here, I'm going to call that C. So we'll say C equals 13 feet. And we could actually label it up here, C equals 13. So that's a consistent, okay? This does not change. Does not change. All right? That's important to understand. Now, our picture is basically a right triangle. As the ladder slides down, the triangle gets longer across the bottom, shorter across the height, but the hypotenuse always stays a consistent 13. So that means that my relationship here is Pythagorean theorem. So if we were to set this up, we would say that we have 13 squared equals h squared plus x squared. Now, you're asking yourself, why did we plug in 13? The reason we can plug in 13 this time is because the 13 doesn't change. H is consistently changing. As the ladder falls, H changes. As the ladder gets pulled out, X is changing. So I cannot plug in for H or X if they are changing. Now we'll take the derivative. So we're going to take ddx, or excuse me, ddt of 13 squared equals h squared plus x squared. Well, the derivative of 13 squared is just 0. So the left side 0. The derivative of 2h, or excuse me, of h squared is 2h dh dt. dh dt. And the derivative of x squared is 2x dx dt. So at this point, I want to know, do I have enough to plug in what they gave me or what I had given to me at the beginning? So I need to know h, okay? I need to know h when x is equal to 5. That was part of the given information, okay? Now, the reason I need to know h here is because you can see, if I look at my formula so far, it says 2 times h. Well, I don't know what h is. I'm looking for dh dt, so that should be my one variable that's unknown here. I have a variable of x, and I'm told that x is going to equal 5. And then I have dx dt, which I know is 2, for the rate given as 2 feet per second. So I don't have enough to plug in here. You can see that if I try and plug in right now, I would have 0 equals 2 times h times dh dt plus 2 times x, which is 5, and dx dt, which is 2. I cannot solve this because I need to know h. Well, here's the thing. I need to know h when x is equal to 5. Well, guess what? I'm going to go back to my picture for a minute. If x is equal to 5 up here, that's a right triangle. I can find out what h is by using Pythagorean theorem. So I'm going to do that. So I'm going to do 13 squared equals h squared plus 5 squared. Well, 13 squared is 169. 5 squared is 25. So if I subtract 5 squared off of both sides, I get 144 equals h squared. So that means that h is equal to 12. So at the point when x is 5 feet from the wall, when the base of the ladder is 5 feet from the wall, that means that my ladder is 5 feet high off the ground. Okay? So at that instant, so now I can take out my h and I can plug in 12. So this is going to be 2 times 12 times dh dt plus whatever we got over here. So this is going to be 24 dh dt plus 10 times 2 is going to give me 20, and now I need to solve for dh dt. Okay, so I'm going to come back up on the right side here. We're going to subtract 20 on both sides here, minus 20. So now we have negative 20 equals 24 dh dt. We'll divide out 24 on both sides. That's negative 20 over 24 equals dh dt. And then we can simplify this. So dh dt is equal to, and that's going to be negative 5 over 6. Now we need some units in here. Our units were in feet. This is a distance from the top of the ladder to the ground, and our time was in seconds. So our ladder is falling negative 5.6 feet per second. Now if it says to explain the results, we would say that the ladder, or more specifically, the top of the ladder, because that's what was asked in the question. So the top of the ladder is falling at a rate of 5.6 feet per second when the base of the ladder is 5 feet from the wall. Now, as you saw in the video, in the applet, as the base got further away, the top of the ladder fell faster. Okay, and I showed you some of those rates in the applet. But so at this point, my ladder's falling fairly fast, and as the base of the ladder goes further to the right, my ladder will fall even faster and until it hits the ground.